In this video, we're going to look at eigenvalues and eigenvectors. So we're going to define what an eigenvector value is, or we are going to review it for those who have had linear algebra already. So an eigenvalue and eigenvector of a matrix. Suppose that A is a square matrix of size n, and x is not a zero vector, and x is in the complex, which just means that my values in each entry is complex or real, and lambda is a scalar in the complex. Then we say x is an eigenvector of A if with an eigenvalue of lambda if this is true. A, the matrix A multiplied by x, ends up becoming lambda multiplied by x. These are vectors, by the way. X's are vectors. Every matrix has an eigenvalue. So suppose A is a square matrix, then A has at least one eigenvalue. Characteristic polynomial. Now this is something slightly different than what we have in our regular characteristic polynomial when we're talking about homogeneous linear coefficients of second order differential equations. This is a different kind of characteristic polynomial. Now we're talking about the characteristic polynomial of the matrix A. It is defined as the determinant of the matrix A minus x multiplied by the identity matrix of size n. If we replace x with lambda in the above equation, we now have the tools to find the eigenvalues. So let's go through and find some eigenvalues for this given matrix A. Matrix A is 3, 3, 6, negative 4. So the first thing I'm going to do is determine what A minus lambda I would look like. Well, this would be 3 minus lambda. Now I is the identity matrix, so lambda I would look something like this, lambda 0, 0, lambda. So we're using a 2 by 2. So it's 3 minus lambda, and then we have 3, and then 6, and negative 4 minus lambda. Now let's do the determinant of the A minus lambda I. So this determinant then is going to be, well, it's going to be 3 minus lambda multiplied by negative 4 minus lambda minus 3 multiplied by 6. So I am just going to go ahead and multiply this out, and when I do, I get a lambda squared minus lambda, or plus lambda minus 30. So if we were to factor this and set this thing equal to 0, we'd have lambda minus 5, and we'd have lambda plus 6 is equal to 0. That means I get lambda is equal to 5, and lambda is equal to 6. So we have found, or negative 6, we have found our eigenvalues. Now we're going to find the eigenvectors in a moment. We're just going to be able to find our eigenvalues. Here's our first theorem. It says, theorem of eigenvalues of a matrix are roots of the characteristic polynomial. So those eigenvalues are the roots, which we kind of expected. Let's go ahead and find the eigenvalues for this. Now remember, it's going to be the determinant of. What we know is it's going to be 2 minus lambda minus 1, and negative 1, and then 2 minus lambda. Now doing our regular multiplication, I'm going to get 2 minus lambda, the quantity squared, minus 1. And so I'm going to multiply everything out, and I'm going to get lambda squared, minus 4 lambda plus 3. Which then factors into lambda minus 1 and lambda minus 3. So we have the lambda is 1 and the lambda is 3. Now, it didn't ask for the eigenvectors, but I'm going to go through how to find the eigenvectors. We found the eigenvalues. Now let's find the eigenvectors. Now, what we know, starting with lambda is equal to 3. We know that 2 minus lambda and the negative 1, and the 2 minus lambda is going to be equal to, using that 3, is going to be equal to negative 1, negative 1, negative 1, and negative 1. Now, this is going to be a row equivalent. If I do the row reduced to echelon form, would be equal to 1, if I just add these, do the subtraction of these two, would be -1, -1, 0, and 0 in those positions. So I know I've got one pivot and one free variable. And so starting with this, I have x sub 1, negative x sub 1 minus x sub 2 is equal to 0. So negative x sub 1 is equal to x sub 2. So x sub 1 is equal to negative 1x sub 2. So my relationship, or my vector, now in the first position, x sub 1 is negative 1x sub 2, and x sub 2 is itself. So this is the eigenvector. I'm going to call it v1. That's associated to that first lambda value. Let's do the same thing here. So we have lambda is equal to 1, and I end up with lambda is equal to 1. I'm going to end up with 1, negative 1, negative 1, 1. If I row echelon this, I'm going to get 1, negative 1, 0, 0. That tells me that x sub 1 minus x sub 2 is equal to 0. That means x sub 1 is equal to x sub 2. And I'm going to call this v sub 2. Its vector is going to be 1, 1. And that's because 1 times x sub 2 is x sub 1, and x sub 2 is in terms of itself. We call this the null space. So if you've had linear algebra, we're basically finding the null space for this given vector. So I found the eigenvalues and the eigenvectors. Now let's take a look at my next example. Let me move this all up and out of the way. And we're asked to find the, I'm going to do the eigenvalues and the eigenvectors for this as well. So we know we're going to do the determinant of a minus lambda I. So I have the determinant of, it will be 3 minus lambda, 3, 6, negative 4 minus lambda. And for this, we have got, this is going to be x squared plus lambda minus 30, because it's the one we started out with. And so we know that the lambda is going to be 5, and the lambda is going to be negative 6. Now again, we started out with this. So let's then find the eigenvectors associated to this. So we found the lambdas. Let's start with lambda is equal to 5. Then 3 minus lambda and 3, and 6 and negative 4 minus lambda, using lambda is equal to 5, becomes, let me just erase this. This will become negative 2, 3, 6, and negative 9. Now you can see that one row is a multiple of the other row. If I multiply the top row by 3 and add it to the second row, I'm going to have a row echelon equivalent form of negative 2, 3, 0, and 0. So this tells me that negative 2x sub 1 plus x sub 2 is equal to 0. So my relationship is this. X sub 1 is going to, and that should be a 3. 3 over 2 x sub 3, and so my vector, we'll call it v1, is going to be equal to x1 is 3/2 x sub 2, and x sub 2 is going to be 1. And this should be x sub 1. Again, we're finding the null space. Now let's do with the lambda is equal to negative 6. Lambda is equal to negative 6. So I'll have 9 and 3 and 6, and I'm going to have, let me see, negative 4 plus negative 6 plus a negative 6, so that gives me positive 2. So that's what I end up with. And you can see when I reduced echelon form this, that since I have the first row, let me see, if I took the first row and multiplied it by 3, and I took the second row and multiplied it by a negative 2, I'm going to end up with 9, 3, 0, and 0. So that tells me that 9x sub 1 plus 3x sub 2 is equal to 0. That means x sub 1 is equal to negative 1/3 x sub 2. So my second vector, my eigenvector for the negative 6 is going to be negative 1/3 and 1. Just as a friendly reminder, what the hell is the null space and where am I getting these numbers? Basically, this position is how x sub 1 is expressed in terms of x sub 2, and this position is how x sub 2 is expressed in terms of x sub 2. That's why it's going to be 1 always in those positions. Okay. Now, what happens when I have a multiplicity on my eigenvalue? So it's not just my previous examples, I had nice lambda's 5 or lambda's equal to negative 6. I didn't have a multiplicity. So suppose that that A is a square matrix, and that should be the matrix A is a square matrix, and lambda is an eigenvalue of A. The algebraic multiplicity of lambda, alpha A of lambda, is the highest power in which I have x minus lambda that divides the characteristic polynomial. And then the definition of a geometric multiplicity of an eigenvalue is, so suppose that A is a square matrix and lambda is an eigenvalue, then the geometric multiplicity lambda, and notice that this is a gamma sub A of lambda, that should be lambda, is the dimension of the eigenspace denoted E sub A of lambda. Note, every eigenvalue must have at least one eigenvector associated to it. And so for the given square matrix, find the eigenvector, the corresponding scalar R, so this makes it true. So I believe I've already done the first one, so I'm going to skip that. So let's go to the second one. This one I did in my previous example. Now I'm going to do this one. So we know that this is going to be then, and before I do that, I need to make a correction. This should be a negative 6 right there. So when I do my determinant of A minus lambda I, we know this is going to be the determinant of, I'm going to have 2 minus lambda, 7, negative 1, negative 6 minus lambda. This then becomes the 2 minus lambda multiplied by negative 6 minus lambda plus 7, which ends up becoming lambda squared minus or plus 4 lambda minus 5. This factors into lambda plus 5 and lambda minus 1. So I'm working with a lambda is equal to negative 5. My 2 minus lambda, it's terrible, 2 minus lambda, 7, negative 1, negative 6 minus lambda, ends up becoming 7, 7, negative 1, and negative 1, which then row reduces to 1, 1, 0, 0. So this tells me that x sub 1 plus x sub 2 is equal to 0. X sub 1 is equal to negative x sub 2. So my vector is, in the first position, x sub 1 is negative 1 x sub 2, and x sub 2 is in terms of itself, so that's 1. Now looking at the lambda is equal to 1, my 2 minus lambda is going to give me 1, 7, negative 1, and then again negative 7. So row reduced to echelon form gives me 1, 7, 0, 0. And so I have x sub 1 plus 7 x sub 2 is equal to 0. X sub 1 is equal to negative 7 x sub 2. So my second vector, my eigenvector, this is 1 and this is 2, it's going to be negative 7, and 1. Now let's take a look at this next example where I have got negative 4, negative 17, 2, and 2. So I'm going to have the determinant of A minus lambda I is going to be the determinant of negative 4 minus lambda, negative 17, 2, and then 2 minus lambda. All right. Now, this ends up becoming negative 4 minus lambda, 2 minus lambda, plus 34. This ends up becoming lambda squared plus 2 lambda plus 26. This is complex. So my lambda 1 and my lambda 2 are going to both be negative 1 plus or minus 5i. Well, one and then the other. So let's start with the complex one because, yeah, that's fun. Lambda sub 1 is equal to negative 1 plus, let's do the positive 5i. We'll start with the positive first. Now, we know when we put that in to this, we're going to get negative 4 minus negative 1 plus 5i, negative 17, 2, and then 2 minus a negative 1 plus 5i. Now, this ends up becoming, just kind of combining up like terms, I'm going to get negative 3 minus 5i and negative 17. I'm going to get 2 and then 3 minus 5i. Now, my goal is to get 0 here. So if we take and multiply this row by the conjugate, well, actually, we'll multiply it by this, and then we multiply the first row by a 2, then what we end up with, so what this is, I'm actually going to do it this time. So I'm going to take negative 2 row 1 plus negative 3 minus 5i row 2 back into row 2. I just want to show you that you're going to get zeros there. When you do this, you're going to get negative 3 minus 5i minus 17. Now, this is going to be negative 2, negative 3 minus 5i, and then this is going to be negative 17 multiplied by negative 2. This multiplication is 2, negative 3 minus 5i, and this is going to be negative 3 minus 5i. Now, you can see these two, when they add together, are going to be opposite, so we know that's going to be 0. So that's nothing surprising. Now, let's do this other multiplication here. So I know that when I do 3 minus 5i multiplied by negative 3 minus 5i, this is the same thing as 3 minus 5i multiplied by negative 1 multiplied by 3 plus 5i. And you can see that these are conjugates, that this is a conjugate of this. So what I really have is going to be equal to negative 1 multiplied by the conjugate. Well, the conjugate is going to be 9 plus 25. So this is going to give me negative 34. Now up here, this is a positive 34, so that's also going to give me 0. So these are row reduced echelon form equivalent. Now, what do we have? Well, from this first row, we have x sub 1 multiplied by 3 minus 5i minus 17x sub 2 is equal to 0. And that should be a negative 3. All right. That means x sub 1 is going to be 17 divided by negative 3 minus 5i, x sub 2. Well, we're not going to leave the complex number in the denominator. So now we're going to kick back and do a little bit of algebra. So 17 over negative 3 minus 5i. And so what we're going to do is multiply by its conjugate, which is negative 3 plus 5i, and negative 3 plus 5i. When I multiply by its conjugate, I'm going to get 17 negative 3 plus 5i. And then in the denominator, I'm going to get, let me see, 17. We know that this is 34 because we did the conjugate just a few moments ago, which gives me, if I pull out a negative, I'll get negative. The reason I'm going to pull out a negative here is because I just like to have a positive 3. So it doesn't matter. You don't have to. 17 divided by 34 is 1/2. And then I can write this as 3 minus 5i. So its eigenvector v sub 1 is going to be equal to negative 1/2, 3 minus 5i, and 1. I'm going to do something similar for the other eigenvector. So I did the first one, which is the -1 minus 5i. Now I'm going to do the same thing when I have, I'm going to call this eigenvector 2, which is -1 minus 5i. Going through the same process, I will just give you the answer. And my v sub 2 is going to be equal to -3 minus 5i divided by 2 and 1. Now, if I don't like these fractions, I just want to say that if I don't like these fractions from my eigenvectors here and here, so these two, I can multiply by 2 because I have that scalar. So if I don't like to see that 1/2, then I can just rewrite this as -3 minus 5i and then the 2 in that position. I'm good either way. Now, let's take a look at D. D is a little bit more involved, and there should be a 2 right there. Otherwise, this is going to be more difficult. Anyways, let's start out with our determinant of a minus lambda I. When we do that, we're going to get 1 minus lambda, -2, 1, -1, negative lambda, 1, -1, -2, and 3. My characteristic polynomial, by the way, when I multiply this baby out, is going to be actually not bad. It's going to be negative lambda to the third plus 4 lambda squared minus 4 lambda. Now, if I factor out a negative lambda, I'm going to get lambda squared minus 4 lambda plus 4, which actually isn't too bad. And that gives us that lambda is equal to 0. Oh, I should probably factor this a little bit more. It's a perfect square trinomial. So I get negative lambda, lambda minus 2, the quantity squared. So we get lambda is equal to 0, and lambda is equal to 2 with a multiplicity of 2. So I'm going to show you how to deal with that. Let's start with the first one, though. Let's start with the lambda is equal to 0. And so my matrix, of course, is 1, -2, 1, -1, 0, 1, -1, -2, and 3. Now, this is going to row reduce, and it's going to row reduce rather nicely into 1, 0, 0, 0, 1, 0, and -1, -1, and 0. My x sub 3 is my free variable. X sub 3 is the free variable. So starting with this first row, I'm going to get x sub 1 minus x sub 3 is equal to 0. So x sub 1 is equal to x sub 3. From the second row, I'm going to get x sub 2 minus x sub 3 is equal to 0. That means my x sub 2 is equal to x sub 3. So my vector, my eigenvector that's associated with this, I'll call this v sub 1, is equal to, well, x sub 1 is 1 x sub 3, x sub 2 is 1 x sub 3, and x sub 3 is 1. So it's the null space. Yay, null space. Okay, now, what happens when I have x sub 2? Well, it's a repeating variable, so this is the vector, so or the matrix, so we have the lambda is equal to 2. My matrix is going to look like this: -1, -2, 1, positive 1, -1, -2, 1, -1, -2, 1, which you can see when I row reduce this, I'm going to get this: 1, -1, -2, 1, and then zeros everywhere else. So I have one pivot, which means I have 2 free variables. My free variables are the x sub 2 and the x sub 3. That means I'm going to get 2 vectors associated. So starting with this first row, x sub 1 plus negative x sub 1 minus negative x sub 1, let's try this again, negative x sub 1 minus 2x sub 2 plus x sub 3 is equal to 0. So I have negative x sub 1 is going to be equal to a positive 2x sub 2 minus x sub 3, which means x sub 1 is going to be equal to negative 2x sub 2 and then plus x sub 3. So starting with the x sub 2's, x sub 2, I have a -1 or -2 x sub 2 is equal to x sub 1. X sub 2 is in terms of itself, and x sub 3 is not available. My second vector that's going to be associated to this is that x sub 1 is 1 x sub 3, 0 x sub 2, because x sub 2 is not in terms of x sub 3, and x sub 3 is in terms of itself. So because I had that multiplicity of 2, I ended up with 2 eigenvectors for the one eigenvalue because it had a multiplicity of 2. All right, so let's take a look at our next example. So we have this matrix, and determine if u sub 1, u sub 2, and u sub 3 is an eigenvector for A, and if they are, find the associated eigenvalues. The easiest way to check is that we know that A multiplied by the u must be equal to some alpha multiplied by that vector u. That's the easiest way to tell. So let's start with A multiplied by u sub 1. This is going to be equal to 3, 5, 4, and 2 multiplied by 5 and 4. And when I do this, I end up with 35 and 28, which is 7 multiplied by 5 and 4. So yes, u sub 1 is an eigenvector, and the lambda, the eigenvalue, happens to be 7. Now let's do this again. Let's do A multiplied by u sub 1, or u sub 2. So I have 3, 5, 4, and 2 multiplied by 4 and negative 1. And when I do this, I get 7 and 14. Now there is no way I can get 7 and 14 to be a multiple of 4 and negative 1. So this one is not an eigenvector. Let's try our last one. A u sub 3. 3, 5, 4, and 2 multiplied by negative 1 and 1. And I end up with 2, negative 2. So we know this is negative 2 multiplied by negative 1, 1. So yes, this is an eigenvector, and in fact, my lambda is equal to negative 2. We like those. Those are always easier. But it's easier to check than actually to find them. Now, some important outcomes that we get from our linear algebra and from this section are here. I'm just going to let you read through them. Go ahead and pause and read through them, and we'll talk about them in class if you have questions. Otherwise, that's it for this video.